Okay, I believe we should be live now, and I'm dropping the link in the chat as usual. So there's that link to the chat, or from the chat to the live stream. Okay, so let's go ahead and start class. Sorry we are a few minutes late, but that's what happens when I have to be my own tech support in a broken classroom that continues to not get fixed. So we are back today with our content, and we are starting a new section in the notes. But first, a quick announcement is that I will be posting the first homework later today, so keep an eye out for that when that gets posted. That will be due in 2 weeks on that Friday by the end of day. Okay, so you guys will have full 2 weeks to work on that. Yeah, we've covered enough material now that we can start sort of assigning questions. The homeworks might still sometimes have a tiny bit of material from the next lecture, like after this one or maybe the one after that, but like the majority of it you should be able to do by now. And then yeah, and we'll try to make it so that you'll still have plenty of time after. So like we won't put stuff on the homework that we'll cover right before it's due, right? We'll put stuff on there that you guys will have plenty of time to work on before the deadline. Okay. So yeah, so let's go on to the next topic. The next topic we are covering in this class, we're going to be talking about Monte Carlo methods, which is a really nice sort of computational tool for solving complex problems that are either very difficult or sometimes even impossible to solve in an exact analytical way. Monte Carlo is a series of sort of computationally based approximate methods for solving problems, but usually a pretty close approximate solution is oftentimes just as good as an exact one in the real world. So that's what we're going to be covering today. A little bit of background on this. This was a method that was invented by this guy, Stanislaw Ulam. He was a physicist. He, fun fact, worked on the Manhattan Project next to people like Oppenheimer. And one time when he was recovering from a surgery, he was playing solitaire, and he was trying to figure out the probability that a game is solvable, because not all games of solitaire are solvable. And he came up with this idea of sort of randomly just dealing out decks and then playing them, hopefully with optimal play, and then assuming that you play with optimal play, for each dealt hand, you figure out just if it's solvable or not, and then that gives you an approximation of that probability, right? Sounds kind of simple, but it's actually a very powerful sort of an approach that has tons and tons of applications in the real world. The name is a code name. It's a reference to the Monte Carlo casino. Back then, they were actually using these methods in some of those top secret, like Manhattan Project and other sort of government-funded secret projects. So they needed a code name for this method. So that's kind of what they came up with, and the name has just kind of stuck. Okay, so yeah, Monte Carlo method is just, in general, any sort of a method where you are attempting to derive an approximate solution to a problem by essentially randomly sampling in a certain way and then processing those simulations to get a result in the end. Anything that involves a process of sampling and simulation can sort of be categorized as a Monte Carlo method. Now, let's talk a little bit about sort of some of the notation that we'll be referencing as we are going through these notes here. So let's say we are talking about some event E of a random variable x, right? So x is our random variable. The outcome set is omega. We're talking about some event E that is a subset of omega. Now, So let's say we want to estimate the probability of event E. Now, we are going to generate replicates of the variable x. These are often going to be denoted this way: x subscript 1, x subscript 2, x subscript m. Each of these x subscript i's represent a single drawn observation from x. So, each one of these x's is a sample size 1 observation of x. Together, we have a sample of m repetitions. They're also often called m replicates. Throughout this class, we'll try to use m to denote the number of replicates that we are doing. And we evaluate this function that is often referred to as an indicator function. Indicator function is kind of just like a flag function. Basically, this function, it's often denoted as 1 with a subscript for E. This basically just says, did E occur or not? Okay, so the indicator function is 1 if E occurs and 0 otherwise. Someone can shout this out. What kind of a random variable is this? Let's say we attach a probability P to the outcome 1. What variable is this? Yeah, so this is an example of a Bernoulli variable, right? Because a Bernoulli is a binomial with n equals 1. Something either happens or not. For a Bernoulli, we count the number of successes, just like the binomial. So it's either 1, that means that one trial was a success, or it's a 0, meaning that one trial is a failure. Okay, so that is an example of a Bernoulli variable. So essentially, we turn our x here into this sort of a Bernoulli setup. For each of these observations here, we count it as a 1 and we count it as a 0, depending on if E occurred or not. And then here, we have this step where we are summing these m Bernoulli replicates. So this kind of works out to be a binomial variable. Okay? And it turns out that once we do that sum and then we go ahead and we divide by m, this sort of gives us our sample mean for this binomial variable that we are constructing based off of x. This becomes our estimate for the probability of E. Okay? Now, this kind of naturally makes a lot of sense under a frequentist interpretation of probability, because if you think, I don't remember if we talked about this much in 240, but sort of in the frequentist interpretation, we think of the definition of a probability as sort of like the long-run average likelihood of something happening or not. So this kind of follows directly with that, right? Because we're looking at sort of in the long run, we're imagining we're doing a large number of replicates m. In the long run, how many times does this happen in a given sample of observations? And that becomes sort of our estimate for that probability. Here's a simple example of that. Let's say we are letting x be the normal variable with mean 1 and variance 3. Let's say we're asking what is the probability that we get an observation between 0 and 3. Now, of course, this is something that you guys should be very familiar with doing. If you wanted to do this by hand, you could go ahead and figure out you could standardize 0 and 3, right? So you get the corresponding points on a standard normal that correspond to 0 and 3. So you do 0 minus mean. So in each case, you subtract mean divided by standard deviation, right? So mean is 1, standard deviation is square root of 3. So you could do like 0 minus 1 over root 3, and then 3 minus 1 over root 3, and you figure out what those numbers are. You get the p norm of each of those. You subtract, you can get that probability. You can also just use r to just do, let's zoom in a little bit here. You could do p norm 3, and then make sure to specify the mean and the standard deviation. Remember that sometimes we might give it to you as variance 3. Just don't forget to take a square root of that, right? So variance is 3. My standard deviation is square root 3, right? SD is square root of 3. By the way, if you are worried that you might forget, sometimes just forcing yourself to use the named arguments helps you. So forcing yourself to write out, mean equals 1, SD equals square root 3 can help remind you of that. So this, and then minus the one on the other side, 0, gives us 0.594, 0.594, and that looks good. Okay, so that's one way you can compute that exactly. Now, in this case, this is pretty trivial for us to compute. We can also do this just as an exercise to use this Monte Carlo simulation method. Basically, we just have to do two things. We have to, step 1, generate replicates of x. And then step 2, we figure out how many of these correspond to that event occurring. So we can sometimes, if we wanted to, we can write a function, for example, or we can just write a line of code. That also works. And then we just get the average of those indicator functions. So that's what we're doing here. We have this function that this is that indicator function. We pass it an input, and it says, if it's between 0 and 3, it returns true. Otherwise, it returns false. The true and falses get automatically interpreted by R to be 1s and 0s when you do math with them. So this is totally equivalent for our purposes. So that's our indicator function that we're using. And then the actual, MC generation step here, we set a number of replicates. So that's our, sample size, or our our M number. We're doing 1,000 replicates here. And we just create that initial vector with 1,000 blank spaces to store that. This is often a good step. This helps you save on memory and computation time. In R, don't append. Append is very slow. You should always create that vector beforehand and then store into it. Okay, so we've got that vector of 1,000 zeros. And then we have our for loop just each time for I in 1 to NMC. So for each of those 1,000 replicates, what do? We generate, using our norm, a observation. So this is it's generating one observation. Mean is 1, SD is square root 3. This becomes our single replicate. We can ask whether or not that replicate represents the event of interest happening. So this becomes either true or false. We store that into our vector. And if I just run that, I'm going to just go ahead and copy that and run that in R. So we've got that here. We ran that. We can look at results. We've got a bunch of 1s and 0s. So that looks pretty good. By the way, R automatically converted it as 1 and 0 because our vector is a numeric vector. So R actually converts that 1 and 0 once we try to store that into that numeric vector. And then we just ask for a sum of results over the number of repetitions. You could also get this by just doing mean of results. If you have a vector of 1s and 0s or a vector of trues and falses, you could do mean of that vector, and that gives you the percent of them that are 1. You can see here my result that I got is slightly different than the result in the notes. That's to be expected, okay? Because the Monte Carlo process involves random simulation and generation of these random variables here. Every time you rerun this function, you will get a slightly different value. And that is fine. That's part of the process. This is an approximate solution, after all, right? But you can see here, this approximate solution that I got, 0.596, that's pretty close to our theoretical answer. Our theoretical answer was 0.594. We can figure out the percent error on that. The percent error is we take our result minus the true value divided by the true value times 100. And you can see we have 0.3% error on this result here, okay? 0.3%. So that's pretty good, right? Okay, so that was a relatively simple example where we didn't need that. as we continue on here, we'll go through more and more interesting, more and more advanced examples. But first, I'm going to take a small question break and have a sip of water. Does anyone have questions they want to ask? Again, I can take questions in person or in chat. Nothing in chat right now. Oh, I just realized, I think there's, did I answer these questions before? Oh yeah, no, I answered these questions before. Okay, questions in person from anyone? No? Hope your other classes haven't been having this many technical difficulties. Again, one of the reasons I hate this room, 331, it's a horrible room. We have a question from Ziyan in the chat. Does Monte Carlo have a distribution, or is it just a method? Yeah, Monte Carlo just is a very broad group of lots of methods. It's just methods pretty much that involve like simulation and computation based off of that. So it's a big umbrella term. Okay. The distribution here, if you're asking like for the data set that we're drawing, the distribution that we use depends on the question, right? For this question, our distribution involved sampling from a normal variable because that is sort of what the question is asking us to do. So sometimes it might be explicit like this. Sometimes it might not be so explicit, and we have to generate our own, come up with our own sort of sampling method. And in the next few examples, we'll see a couple of those. Okay? Yes?
Will the Monte Carlo distribution of results, if we run Monte Carlo a bunch, be normally distributed about the true proportion?
Yeah, so the question is, will that result be normally distributed? So if the thing that you are doing in the process of this method involves taking a sum or an average of a bunch of different variables that have finite variance, then usually with large enough sample, it should approach a normal. That's just the CLT, right? If what you're doing is not a sum or mean of a bunch of independent things with finite variances, then it might not approach that. Okay, so it depends on what you're doing exactly. Okay, we'll see examples. We'll see lots of examples where that might not actually even be a question that you even really care about. Okay, whether or not it approaches a certain distribution or not. Good question, though. Any other questions? Yes.
Can you explain again what you mean by you're generating replicates of X?
Yeah, right. So the question is, can I explain again what I mean by I'm generating replicates of X? So it's kind of buried a little bit inside here, but what we're doing here, if you look at my screen, I know there's a few seconds of delay, but hopefully you're on the same page now. So when you're looking at this code here, there's a step where we are saying over and over again, so 1,000 times, repeat this step. What step we are repeating is we are using rnorm, right? So rnorm is generating that random observation, okay? By the way, the code that we're writing here is very, very not optimal. The much better way of doing this is just to do rnorm 1,000, right? So the much better way of doing this is you can do just rnorm 1,000 and then 1√3, and then you just go ahead and you can just say for this vector of randomly generated things here, are these between, there's a between function that I can use I don't remember off the top of my head what package it's in. That's okay. I'll just say this as x, and we can ask, is it true that x is greater than 0, and also x is less than 3, and we get a bunch of trues and falses, and then we can just go ahead and just ask mean of that vector, and that tells me that value. Okay, so this is much better way of doing it. Using this way, using this R norm with n as 1,000 is better because this is doing that operation in a vectorized way. Okay, vectorized operations are always faster. But essentially, at the core of it, what we're doing is we're generating all of these numbers here, and we're using these randomly generated numbers to try to approximate that result. Does that make sense? Yes. Other questions? I think there's one in chat. Oh, no, that's it. Okay. Anything else before I move on? Does anyone have any fun weekend plans? No? Anyone going to the football game tomorrow? I'm going to. I'll see you guys there. Hope we win. Do I mind explaining the indicator function? Not at all. So yeah, the indicator function, it's basically just saying, did the thing happen or not, right? We generate a bunch of these X observations, right? We're like drawing X observations in our sample. And for each observation, we just ask, did E happen? Right? E represents an event. What event we define depends on the question. For this question, we're asking, what is the probability that X is between 0 and 3? That's the question that we are being asked. If we're being asked that, then it might naturally make sense to define this as the event. So our event is X is between 0 and 3. That's the event. Right? Remember that an event is a set of possible outcomes, right? 0 to 3 represents a range of possible outcomes. So that's our event. We define that as E. For each number, we just ask, so like for example, for this number here, we can ask, did event E occur? No, it didn't, because 4.17 is not between 0 and 3, okay? For the next one, did event E occur? Also, no. For the next one, did event, oh, whoops, I lost my place there. For the next one, did event, what is, magnifier class is so stupid. Okay, sorry. For the next event here, did event E occur? For this one, it did. 1.6 is between 0 and 3, right? So for each number, we're asking, did event E occur? And it turns out if we represent that as a bunch of trues and falses or ones and zeros, and then we just ask for the average of those, that turns out to give us an estimate of the probability. Okay, hopefully that makes sense. I do want to continue though. We'll go over a few more examples of increasing interestingness. So the next example here, we've got some of you might have heard of this, it's called the birthday problem. It's kind of a well-known, sort of a counterintuitive problem in probability and statistics. The birthday problem is this problem where, let's say we have a group of n people. What is the probability that 2 or more of them have the same birthday? Can I get a volunteer from someone in the front couple rows just to help me with the task? I promise it's very easy. Can I get a volunteer? Yes, okay. Can you count, so I'm going to keep going. Can you count all the people in the class, including yourself, and tell me how many people are here, okay? Thank you. I will keep going while he counts. So in a group of n people, what is the probability that 2 or more of them have the same birthday? It might seem like it'll be very low, but actually the counterintuitive thing is that if we don't specify, if like a predetermined day that we are looking for, if we're just asking for 2 people having the same birthday, actually that probability becomes pretty high. It turns out that around a group of 23, that probability becomes about 50%. So in a group of 23 people, there's just over a 50% chance that 2 people share a birthday. Okay? Kind of weird. We can approach this in 2 ways. This is also, we can compute this in an exact way. It's not that hard to compute this. Basically, for each person, we just ask, what is the probability that they have a birthday that is different from all the previous people, right? So for the first person, well, any date that they have is going to be unique. If we're just starting with one person, let's say we add one more person into the room, well, one birthday has already been taken by that first person, so the probability that the second person has a unique birthday is 364 out of 365, okay? And then once we add a third person into the room, the probability that he or she has a different birthday than both of the previous people is 363 over 365. So you keep going down each additional person, you reduce the top number by 1, and you keep the bottom number the same. Of course, we are assuming independence there and uniform distribution. So we're assuming that every date of the year is equally likely to be someone's birthday, which is definitely not true, but we're making that just as a simplifying assumption. We're also assuming that people's birthdays are independent of each other. Also probably not totally true, but also just a simplifying assumption. Making those assumptions here, if you compute this all the way down, it turns out that result grows pretty quickly. Okay, so what is the count of people in the room?
Somewhere between 52 and 48.
Okay, thank you very much. What's your name?
Edward.
Huh?
Edward.
Edward? Okay, everyone thank Edward? Okay. So let's say we have about 50 people in the room. Let's just do this computation for 50 people and let's see what we get, okay? So we want to go from 365 all the way down until we have 50 numbers. So that means that we want a sequence of 365 and then if I just minus 50, I'll have 51, but that's approximately fine. So let's say I'll just go down to 315. So we have roughly 50 people. And you can see that is, yeah, that looks good. I'm going to take each of these and divide by 365. So each of these represents one of those fractions, and then I just multiply them all together. To multiply them, there's a function called prod. Prod just takes the product of all of these. So this computes the probability that every person has a distinct birthday. So that's the probability that everyone has a distinct. The probability then that at least 2 people have the same birthday is 1 minus the probability that everyone has a distinct birthday. So there is a 97.4% chance, roughly speaking, that 2 people in this room share the same birthday, okay? So you would definitely be willing to bet a lot of money that 2 people share a birthday. Kind of a fun fact. Okay, now let's go ahead and show this in a more concrete setting because it still feels kind of surprising, right? How do we go ahead and kind of just show that as an extra step to make sure that that feels kind of sensible? So we can run this, here we go. So we can run this function here. And I'm going to break this function down and just run this sort of line by line. We start by using the sample function. We're going to be using the sample function a lot more in this class. So it might be worth taking an extra minute to talk about the sample function. I'm going to go ahead and do that now. The sample function is a base R function that is used for drawing samples from a given input that we are providing it. Sample actually has 2 functions. You could either use it by just giving it a number as the input. So if I just write, for example, if I just write sample 10, what sample 10 actually does, sample will detect that the given input is just a single number. It is not a vector of things, and it will run the sample int function. Whenever you see in a help page that there's multiple versions of a function that are distinguished by dot something, that's just R's way of telling you that it will run these different other functions depending on what the input is for the base function, right? So if you give x as just a number, it'll actually run sample.int and use the input x as n. So when I run sample 10, it sets that as 10. And then by default, it sets size equals n. So this will give you, this will randomly choose a vector of size n out of the numbers between 1 through 10. By default, replace is false, which means it does so without replacement. So if I just do sample 10, you can see what it does here. It just shuffled the numbers between 1 and 10 and printed them out, right? So it gives me 3, 2, 4, 1, 8, 7, 5, 6, 10, 9. You could also give sample a vector. You could give it actually, sorry, before I show the vector use, let me show the other arguments. If I set replace equals true, remember that true and false in R always has to be all capital. So all capital true or all capital false. If I set replace equals true, we are now allowing replacement. So every time it takes a number out between 1 and 10, it puts it back before it draws the next one. Now we see we have some repetitions. We have 2 10s, we have 3 copies of 3, and we're missing, of course, some of the numbers between 1 and 10. If you are setting replace equals true, you can also set a higher size if you want. I could say, for example, size is, let's say 100. I draw 100 times a number between 1 and 10, and I put it back each time. Okay? If I set size as 100 without setting replace as true, it will give me an error. Okay? Because it can't do that without replacement. But if I set as a smaller number, if I say set size as 5, it can do that. So this one is done without replacement. We're just drawing 5 numbers. Okay? All of these things also work if the input is a vector. So I could say, for example, if I wanted to simulate, let's say, heads and tails, right? Drawing from a coin, flipping a coin, I can go ahead and I can create a vector C with H and T. I can say size is, I don't know, let's say 50, and then replace, obviously we need to set as true, and that gives us a bunch of those, okay? So that is sample. There's one more argument here, prob. You can use prob to set a probability distribution for those values. The prob thing that you get, you can technically give it as any kind of a weight thing there. So what that means is, it just does like a weighted sampling of those different options. And I think if it doesn't add up to 1, it'll automatically normalize that for you, if I remember correctly. So that's the sample function. We're not going to use any of those super fancy functions or sort of sub-methods right now. All we're going to use is just size and replace. So we're going to sample from 365, size equals n, replace equals true. The reason that we're doing this is we're letting each day of the year be represented by a number. So 1 represents January 1st, 2 represents January 2nd, all the way down. 365 represents December 31st. We're ignoring leap years for now. And let's say I do this with n equals 50. So we have about 50 people in the room. So size is 50, replace has to be true, right? Because we can have multiple people being born on the same day. So if I run this, you can see it just randomly generated out 50 of those birthdays. And I can ask, do we have any duplicates in here? So let's say I save this as dates, as a vector called dates. I can ask, are there any duplicates in that vector there? An easy way of doing that is we can use the table function. So table will tally up and tell you how many times each thing is observed, right? So if this is dates, table of dates will tell me that I have 1 observation of the number 3, I have 1 observation of the number 5, all the way down. And I can see already we have a duplicate. We have a duplicate for 141. So whichever date that corresponds to, that is a duplicate. In fact, I can pretty easily find that. I can say, let's see here. I want to do, if I just import tidyverse, I can go ahead and YMD, and I'll just say 2022-12-31st. If I start counting from this, if I add 1 date, that gives me January 1st, right? If I add 2 dates, that gives me January 2nd. You can just ignore the year, that doesn't matter. If I add 141, that is May 21st. So in our representation here, we found 2 people that were randomly generated here that had the birthday of May 21st. Now, Once again, in this step here, we're making some assumptions, right? We're assuming that there's a uniform distribution of birthdays. We're also assuming that these are drawn independently. In the real world, those are probably not exactly true, but this is just a first order approximation. Okay, so now I can take that code, which, by the way, when you do table of dates, the result of this is just a vector. It's a vector with a name. Okay, so this is a named vector. It's not a matrix or anything like that. You can drop the names. If I do unname, that drops names. You can see it's just a simple vector. You can also set, I believe, names as false in one of the arguments. I don't remember off the top of my head what that argument is. But yeah, so you could ask, for example, because this is just a vector, you could ask what the maximum of this is. So max of table dates will tell me the largest number of counts for a given date. And you can see here this is 2. Okay, so if that max is 1, we have all unique. If that max is larger than 1, we have at least 2 people that have the same birthdays. So that's why we're doing this max of table greater than 1. If you repeat that process over and over again, we can just go ahead and see. Let's just say we go ahead and I'm going to just sample again from this. So sample from that. And I'm just going to just put right into here max of table of sample, and is that greater than 1 or not? So this is sort of a one-line way of checking that. And we have true, true, and you can see most of the time it's true, right? One time it was false, but most of the time it's true. How often is it true? You can go ahead and put that into a function. So here we define this as a function, and then we run that function over and over again. There's kind of a shorthand way of doing this that you'll see me using in lecture a lot. If you have something written as sort of like a one-liner, which I have a bad habit of doing, but if you have this one-liner here that gives you a true or false, you can wrap that in a what's called a replicate function or replicate, and I can just say 1e, let's say 1e4 for 1,000. This will just run that 1,000 times, and you should be able to see here that is my result. I can save that in a vector called x because I don't want to think of another name for it. So that is my vector there. What is the mean of x? That tells me the percent of them that are true, and that is 0.971. Okay, so that's pretty close to our theoretical value there. What was our theoretical value before? It was, let's see here, 1 minus prod of that. It was 0.974. So once again, if we want to, we can figure out our error on that computation. The experimental minus the theoretical divided by the theoretical times 100. That's, again, a percent error of about 0.3. Okay, so that's a pretty good approximation. And you can see here, it might seem surprising, but it's almost guaranteed that 2 of you guys have the same birthday right now. So that is the birthday problem. Okay, let me take another short break if anyone has more questions. I know we're also pretty close to end of class. Questions on any of this stuff so far? No? Okay, I'm going to end class by talking about this last little bit of a theoretical basis of this. This is also something that I don't really expect you guys to necessarily become expert in or like memorize or anything like that. Just want to kind of briefly explain why this works. The short answer is the law of large numbers makes this work. The longer answer is that we can represent our probability of the event happening. So probability that E happens. If you go back to the random variable page, you can see that you can represent the probability as an area under the curve, right? So it's always you find some area that represents the corresponding range of outcomes that you are interested in. So, and then that area under the curve you can represent as an integral of a certain region of your density function. So that's what this is saying. This is saying find the area under the curve in that given range that you care about, right? It turns out that we can sort of play with that a little bit here. We can change the integral range to be the entire outcome space, and instead we insert an indicator function. The indicator function is only 1 when we are inside that range S that we care about, and it is 0 everywhere else. So these two formulations are equivalent because this integral, this integrand is 0 when it's not inside that range S. Okay? When it's inside S, that's just a 1. Now, it turns out that this is the formulation for the expectation of a function. Because, again, this is something that we didn't really cover in detail, but if you recall the expectation formula for a discrete result is you take the outcome multiplied by the probability for each possible outcome, and then you sum that. That gives you your expectation. The continuous version of that, right, the continuous analog is you do an integral of whatever outcome you are talking about. That outcome here is represented by g. That outcome is multiplied by your density function. That is integrated over the entire range. That's the expectation definition for a continuous variable. So we can kind of compare these two and note that this formulation on the right side here represents the expectation of the integrator, the indicator function. Because we're doing the integral of the indicator function times f, this can be represented as the expectation of that indicator function. So on average, what the theoretical mean of the indicator function is. And we just have one last step here, is if you recall the law of large numbers basically says under certain conditions, we have the fact that our sample mean will approach the theoretical mean, right? As you take a larger and larger sample, the mean in your sample, so this is x bar when you have, when you're looking at that indicator function, right? As sort of like our new sort of variable. So the sample mean of our indicator function will approach the true expectation of that indicator function. And that is why this whole process works. So that's why we take a bunch of observations of x, we run the indicator function, that gives us a sample of that. Then we take our sample mean, and that, under the law of large numbers, will approach expectation of the indicator function, which is equivalent to the probability of the event E happening. Okay? So this process relies in the background on the law of large numbers, which means you can only really do this process when you have an underlying distribution with finite variance. If you don't have finite variance, that's sort of the main condition that can fail this process, then this approach will not work. But that's a pretty easy, it's a pretty low bar to clear. We're not really going to talk about weird anomalous examples where we don't have that property satisfied in this class. That's a more advanced topic. So for the purposes of this class, don't worry too much about it, but keep this in the back of your mind that that's sort of the underlying process of what we're doing here. Okay, that's all the time that I have for today. Thank you guys for coming, and we'll be back on Monday. We'll pick up here where we left off and keep talking about MC methods. I hope you guys have a great weekend, and everyone knock on wood that on Monday the projectors will work, but if it doesn't, I might have to do this live streaming setup again. Okay, see you guys in a couple of days. Take care.